Hello, this is Dr. Gardner. I'm recording a few tutorials to help my students in my chemistry classes do some common things that I'll require them to understand with respect to reading the periodic table in this specific tutorial. Future tutorials will have example calculations as well as naming compounds and so on. But right now I wanted to start with some tips for reading a basic periodic table chart that you might see in the lecture or in the laboratory or in your textbook. Now there are quite a few different ways of writing a periodic table. Some of them are quite exotic and you might argue could be beautiful, but I think you'll see that the current periodic table that's in the front of your textbook is probably one of the most useful versions of writing the periodic table with respect to having meaningful information. Now I'm going to start here with this tutorial as part 1. Later on we will see part 2 of a similar tutorial which will look at electron orbitals, but I'm not going to focus on that this time. Later on in the semester, go ahead and go to part 2 if you're looking for electron configurations and electron orbital information from the periodic table. So first of all, let's look at a picture of the modern periodic table that we are using in the course. I want you to notice that depending on which version of the periodic table you have, the numbers at the top and the letters may differ slightly, though hopefully I will explain today what they mean and what type of references they have for information in the periodic table. Now the color coding can also change. This specific version will be a little different than the version I'm going to show you in a few minutes, but here we have our metals in green, our nonmetals in blue, and our metalloids, also known as semimetals, in kind of a grayish color. Here I want to show you what we might refer to in terminology as rows or columns on the periodic table. Specifically, if I look at a row on the periodic table, let's say we're starting at potassium and our row goes all the way to the right to our 36th element, krypton, which has 36 protons in the nucleus. You can see here that this would be called a period on the periodic table. That's because there's periodic repeating properties that occur in each period. That is why we're organizing them in this fashion. If we want to look at a column, well, usually we will have these organized into elements that have similar chemical properties and similar reactivity. And we will call these a group, or sometimes we'll call them a family. Our textbook uses both terms for this, but just realize if I use the term group or family, we're going to have a single column on the periodic table that we're referring to, perhaps comparing several elements with similar properties. Now next, we want to give these groups or families a few specific names when we're referring to them. One of the first groups that we will learn will be on the left-hand side of the periodic table, and it's going to start below hydrogen. So we're looking at column in group 1A. So the first column on the periodic table all the way to the left-hand side. Now we're going to ignore hydrogen because hydrogen is somewhat unique. It's our only non-metal that we're showing there. Sometimes you'll even see that shown next to helium on the other side of the periodic table. There's reasons for both arrangements. But right now we're going to start at lithium. We're going to say lithium is going to be the first metal. It's color-coded green here on this periodic table. And then the other metals, which are similar with their chemical properties to lithium, are sodium, potassium, rubidium, cesium, and francium. Now we're going to give this family, this group, this column, one specific name. We're going to call this the alkaline metals. You might be familiar with using lithium in different types of batteries for your cell phones, laptops, and other portable devices. Now our second column, 2A, our second group or family, starting at beryllium, will be called an alkaline earth metal. And so that whole group, that whole column, beryllium, magnesium, calcium, strontium, barium on down, it's going to consist of alkaline earth metals. We're going to see here a little bit later that they also form similar charged cations. They will all end up forming +2 charged cations. Now, on the other side of the periodic table, we're going to look at column 17, also labeled as 7A, starting at fluorine, chlorine, bromine, iodine. These will be considered our halogens. So this group we want to know is named as halogens. Now, the last group or family I want you to learn the name of right now in the course will start in column 18, also labeled as 8A here, starting at helium. So helium, neon, argon, krypton, xenon, radon. we'll see those are noble gases. The reason they're classified as noble gases is because they usually exist as monoatomic atoms. They do not react readily with other elements. So they are quite stable in the atmosphere. We can find quite a few of them stable in the atmosphere around us. There are a few other groups and families with specific names. I'm not going to ask that you memorize them at this point, though you will see them on some of the handouts for the course. Now next I want to focus in on just the non-metals. So I'm going to remove the rest of the elements here, and I'm going to color code in yellow. We're going to highlight in yellow here just the non-metals on the periodic table. So let's take a look at them. So here we have hydrogen. Okay, if we look in period 2, which is going to be our second row, right? That's going to be carbon, nitrogen, oxygen, fluorine. We can see our halogens are there, our noble gases are there. We also have phosphorus, sulfur, selenium. Okay, these are all categorized as nonmetals, and they tend to make molecular compounds by sharing electrons in their orbitals to form covalent bonds, what we call covalent bonds. A covalent bond occurs due to electrons being shared between nonmetals usually. So this is where our nonmetals are. Now we're going to look at the next picture I have for you. Will just show you the metals. So I'm going to exclude the nonmetals. I'm just going to show the metals. You're going to see it's going to make up the lion's share of the periodic table here. And they're going to be color-coded in blue this time. So here we have all of our metals currently. They tend to form ionic compounds by forming cations and combining with nonmetals, which can form anions. But where all these blue elements are, these are all classified as different types of metals. Some of them are main group metals, some of them are transition metals, some are inner transition metals. We'll categorize the different categories of metals here in just a little bit. The last section of elements I want you to take a look at are going to be what we call metalloids, also known as semimetals. They have properties in between those of metals and nonmetals, some characteristics of both. Right now we're going to see that there's just a few of these, and they're along this bold line, this stair step that we have here. They're colored in green here, so I have boron, silicon, germanium, arsenic, antimony, tellurium. Okay, so these are my metalloids, also known as semimetals. Their properties are in between. For example, silicon here has quite a bit of luster to it. It would have a very shiny surface, which could be mistaken to be metallic in nature, but we know it's actually from a semimetal with the silicon. However, it also tends to be quite a brittle element and will tend to fracture and break if it strikes a hard surface, which is characteristic of most of our nonmetals if they're in the solid state. So these metalloids kind of had that identity crisis between metals and nonmetals. It's useful to note that as we cross this metalloid line, this bold line here, we tend to, as we go down, we go from nonmetals to metals with respect to characteristics. So we're going to see the greatest variation, the greatest difference in our families and groups as we proceed across the metalloid line. So just realize this is where our families and groups aren't as consistent with their properties. So if we show it all together, here we have our periodic table color-coded with all of the elements. Yellows, nonmetals, blues are metals, green is semimetals, also known as metalloids, okay, with respect to these different sections. Now here I changed our color coding a little bit in order to differentiate between different types of metals. Our blue metals are what we're going to call main group metals or elements. And so let's first of all look at main group elements. They're also known as the representative elements. They are the ones that you'll notice at the top with our numbers are categorized with a 1A, a 2A, and then as we go from, in the second period, as we go from lithium and beryllium and 1A and 2A to boron 3A, carbon 4A, nitrogen 5A, I'm seeing this at the top of each of my groups or families, then oxygen 6A, fluorine 7A, neon 8A. The A columns are all considered main group elements. They're also called representative elements. So if you hear me use that term, main group element, we're looking at these A columns as shown in this periodic table. Or if I ask you to pinpoint a representative elements, we're talking about these A columns. So let's go ahead and take the other elements away right now. So we're not going to look at the transition metals and we're not going to look at the inner transition metals. So these will be categorized in these columns all as main group elements or representative elements. And they're the ones that we will deal with frequently, especially when we're first looking at types of chemical bonding because it'll be a little simpler to talk about the types of compounds we'll form. And then we'll expand on this knowledge later on, talk more about transition metals as we continue on through the course, and then briefly mention some of the inner transition metals like the lanthanides and the actinides as we broaden our horizons with the chemistry of different elements on the periodic table. Now just remember, these tend to be labeled with an A for the main group elements or the representative elements. Now we're going to look at the transition metals next, and some periodic tables will show a B on their columns and some will not. So the one I have shown here doesn't have B's written on these columns, but realize if you see a B column, that's going to represent a transition metal group or family. So let's go ahead and remove everything but our transition metals. So we're going to remove our representative elements, we're going to remove our lanthanides and actinides, the inner transition metals, and here we're showing just the transition metals. You'll notice there's 10 columns here that represent the transition metals that we're looking at. You should see quite a few familiar faces here with respect to chromium, manganese, iron, cobalt, nickel, copper, zinc. We can see silver, palladium, platinum, gold, right? So we've seen quite a few of these. You might remember the capital W is tungsten. Okay, these are all transition metals. Many of them can have a variety of charge states when they form cations, though I'm going to show you just a few of them. In fact, I'm going to show you specifically 3 of them that can have only specific charges when they form cations. Okay, the rest can form a variety of different charge states. Some are more stable than others, but because they can form different charges when they form a positive cation, we will tend to show Roman numerals for transition metals that can have these variety of charge states. Only the transition metals that can have only one charge state would we exclude a Roman numeral when we are naming their compounds. So this is going to be quite helpful going to chapters 3 and 4 of our textbook. So if you look at the periodic table at the front of your textbook, you'll notice the B next to the groups for the transition metals. This is also a reminder that we're dealing with our transition metals instead of the main group elements. Next, I'd like to look at the inner transition metals, also known as the lanthanides and the actinides. So let's remove the other portions of the periodic table to clearly zoom in on the lanthanides and actinides. We're going to remove the main group elements first, right? That's going to be my first 2 columns, my first 2 groups on the periodic table, and then I'm going to remove my last 6 groups on the periodic table. Those are my representative elements. I've removed those now. We're going to remove the transition metals. Okay, so my inner transition metals are going to be the ones shown here in my lanthanides and actinides portions of the periodic table. Let's see where that name's coming from. Let's look back at the transition metals for just a second. So if we look at element 57, that's going to be my lanthanum. And right after 57, if you notice here, cerium, element 58, is occurring right after lanthanum. So we're going to define that period of the inner transition metals as the lanthanides. Okay. Now you notice that there's 14 elements across. This is going to relate to what's going on with their electron orbitals with respect to how many electrons will fill F orbitals as we talk about them later in the course. If we look at element 89, this is actinium. This is where we start the actinides. Right after that, we're going to run into the actinides. You'll notice a few famous faces that we'll talk about frequently in the actinides. We have uranium here is element 92 for 92 protons in its nucleus. We have plutonium with atomic number 94, with 94 protons in its nucleus as well. So if you hear me ask you about a common actinide, you might say uranium would be one of those. So know your lanthanides and actinides. Know these, both of these sections are referred as inner transition metals. Okay, now the next thing I want you to recognize in the periodic table are which elements form a stable allotrope. That's a diatomic molecule. Now if you recall in lecture I mentioned that an allotrope is a stable form of an element, and sometimes there can be several different forms of an element. Okay, so now we want to look at diatomic molecules that occur that form stably with respect to different elements on the periodic table. There's actually 7 you should know. 7 you should know. So you should know that nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all form diatomic molecules. So we have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And if you look on the periodic table, that forms a nice 7. And that reminds you there's a 7th because we've only named 6 so far. So we have hydrogen gas that exists as a diatomic element. So if I'm talking about these elements occurring in their most stable states in nature with a chemical reaction, like if I say oxygen gas burning with a fuel in a combustion reaction, we will usually use the diatomic molecule O2. If I forget to write O2, I would be indicating a monoatomic oxygen atom, which is not as stable as the oxygen in our atmosphere, which forms a covalent bond, forms a molecule that's diatomic in nature. So know these 7 elements occur as diatomic molecules when we're dealing with them naturally. Okay. Now, if we use the periodic table and what we've learned about it so far, we can also determine the charges on a lot of monoatomic ions. First of all, let's define what a monoatomic ion is. A monoatomic ion is going to be a single atom that has formed an ion. An ion will be a charged species which has either gained electrons to form an anion and be negatively charged, or lost electrons to form a cation and be positively charged. So a monoatomic ion has gained or lost electrons with respect to a single atom to form a charged ion from that single atom. So we'll start with monoatomic ions now. In a future tutorial, we'll start looking at polyatomic ions, which have a group of atoms that are charged overall. Okay, so if we look at these monoatomic ions on the periodic table, first of all, let's begin with looking over at our alkali metals. Do you remember where our alkali metals were? They were here in group 1A, right? So we're looking at lithium, sodium, potassium, rubidium, and cesium. You'll notice that the charge of their most stable monoatomic ion, which is a cation, we can see that because they're positively charged, is a +1 charge. It's the same as their group number, the same as the number on the top of the column here. Now, if we want to look at group 2, can you kind of guess what our charge might be? The standard stable charges for monoatomic ions for group 2? Well, we're going to see that the alkaline earth metals form +2 charged cations, the same as the number of the column they are in the periodic table that we're looking at. Now I want you to notice that these metals are making cations. They're losing one or more electrons to form a positively charged species. We're going to notice that metals usually will lose one or more electrons to form cations, whereas non-metals will tend to gain one or more electrons to form anions when we're looking at monoatomic ions. Now the next metal I want us to look at will be in the main group elements, column 13 or 3A. It's a representative element, it's a main group element. We're going to look at aluminum. Now I want you to notice the 3A underneath here. My 3A, that's going to indicate here the charge I also will see on aluminum. It's a +3 charged cation, so that will be easy to remember. So I can start with sodium's +1, right, here to the left on the periodic table, then magnesium forms +2 charged cations. Then as we jump over this gap to the next main group element, aluminum, it forms +3. So that should be easy to remember those. You use the periodic table as a mnemonic device to help you remember the charges on different ions. Now, as we're looking at aluminum, it's a +3. Let's go into the transition metals for a second. Let's kind of take some stairs down from aluminum to the left-hand side. We're going to look at zinc. I want you to notice that zinc has a +2 charge. It only forms one stable cation. So I won't use Roman numerals for zinc, whereas most of the other transition metals we would use Roman numerals when we write the names of their compounds. So you can easily remember that there's aluminum's +3, zinc's +2. It decreased by 1 as I went down and to the left by 1. Now the next transition metal that only forms one possible stable charged cation would be silver. So silver's a +1 charge, so I would not use Roman numerals on it. We would know it always forms a +1 charged cation when it forms ionic compounds, when it forms compounds where it's a cation. Now right below zinc is a transition metal that only forms one possible charge state, and its charge is identical to that of zinc. So it's cadmium. It forms a +2 charge state. So these are a group here of different metals I want you to know the charges on. Now we're going to look at nonmetals next. So as I mentioned before, my nonmetals tend to gain electrons if they gain any electrons at all, and they end up forming negatively charged ions that we call anions. Okay, so if we look at our halogens, My halogens all form a -1 charged monoatomic ion. When there's a single atom with a charge for halogens, we expect it to be a -1 charged anion each. They've actually gained 1 electron to have the same number of electrons as the nearest noble gas to their right. They gain 1 electron. Now, along these lines, if we look over at oxygen and sulfur and selenium and tellurium, they form -2 charged anions. Now I want you to know, how many columns are they away from the noble gases? They're 1, 2 columns away from the nearest noble gases. And so they form -2 charges by gaining 2 electrons to have the same number of electrons as the nearest noble gas. Now if we look at oxygen, well, the monoatomic ion should be a -2, but sometimes it can exist as a polyatomic ion having 2 oxygen atoms with a -2 charge. That would be a peroxide. So we expect if we see a -2 charged oxygen O2 species, that's going to be a peroxide ion. They're not as stable, and they usually will decompose over time to form oxides. So oxides are the ones you'll usually see that -2. Just realize there is a preview to the polyatomic ions where we have the peroxide ion that we're looking at here. Now my nitrogen, you'll notice it's 3 away from the nearest noble gas. So if we count over 1, 2, 3, it shouldn't be surprising, it's following the trend we've been looking at, that it forms a monoatomic ion with a -3 charge. You'll notice that phosphorus also has a -3 charge. Now when we look at these monoatomic anions that we have been observing so far, we usually end their names with an IDE. Most IDE named anions with the suffix have a monoatomic ion where their charge is related to how far they are from the nearest noble gases. So all the halogens will form -1 charged anions, and we change the suffix, the end of the name, to a ide. So fluorine goes to fluoride, chlorine goes to chloride, bromine goes to bromide, and iodine goes to iodide. So the ending changed to IDE. It indicated monoatomic ions. There's only a few exceptions to this. So the majority of the time, if you see an IDE at the end of a name for an anion, it's a monoatomic ion. Now we can also have oxide with a -2 charge, sulfide with a -2 charge. So sulfur is going to sulfide. Selenium goes to selenide. Tellurium goes to telluride. They're all IDEs, monoatomic ions. Now you notice we could have the halogens with a -1 charge. The oxygen family, the oxygen group, have -2 charges with the monoatomic ions. And then if we look at nitrogen, what do you think the ending might go to with respect to the name for nitrogen? How about nitride? Okay. And phosphorus would go to phosphide when we're talking about these monoatomic ions. They're -3 charged here. Now let's go over one more group to the left to where carbon is. So I want you to notice here we're 4 columns away from the nearest noble gas, so we have gained 4 electrons and a -4 charge for carbon, and which might you expect the ending of the name to go to for carbon here as we form a monoatomic ion? I bet most of you predicted it goes to an ide, so we go to carbide with a -4 charge. So these are all monoatomic ions that you should easily be able to remember by looking at their location on the periodic table. Now recall that you will always have a periodic table in your textbook when you're working on homework. You'll always have a periodic table on exams. When I give you exams, usually it's stapled to the last page of the exam, so make sure you take a look at that to help you remember these. Now there are quite a few transition metals that can have a variety of charges. This is what I would wait to the very last for you to learn. Learn all the ones you can see right now up here on this PowerPoint slide. And then beyond that, start to learn some of the transition metals and the variety of charge states that we might have. There's a few representative metals under the metalloid line that have a variety of charges I want you to learn. So for example, lead. Lead can frequently form a +2 charge cation, but it can also form +4. They're both very stable. We'll look at electron configurations later in the course, and I'll teach you how to predict those charges. But for right now, remember, it likes to form +2 or +4. So I'd have to use Roman numerals when I look at the compound name for lead-containing ionic compounds with the lead cation. So here's the lead-2 cation. It could also be lead-4, so that's not the only possible charge state for it. Tin can form a +2 or +4. I want you to notice it's in the same group as lead, the same family, the same column. they form similar charged cations. So if you know one of them, you know the other one. So that's going to help you remember those two. A few others you might look at would be mercury. Now mercury can form a +2 charged cation where there's one mercury atom, or a +2 charged cation when there's two mercury cations. When there's only one mercury atom in the cation, we're going to call that the mercury 2 cation. When there's two mercuries contributing a +1 each, we're going to say it's mercury 1 even though the overall charge is +2. You'll be seeing this again as we start to name chemical compounds. Copper tends to form copper 1 or copper 2 cations. You'll learn that these are referred to as cuprous and cupric ions as well, with an older fashioned naming system. Nickel can form +2 charged cations. It's one of its most stable charge states, but it can form a variety of other charge states. So again, I would have to use Roman numerals to be sure I knew the charge on nickel. Cobalt tends to form +2 or +3 as the most common charge states. We can look at iron, tends to form iron 2 and iron 3. We'll learn this relates to ferrous and ferric species as well with the older fashioned naming. If I don't use the older fashioned naming though, I can just use Roman numerals to indicate the charge state in compounds that have these cations. Then I have manganese here. Be careful not to confuse manganese with magnesium, which is one of our alkaline earth metals over here. So this is manganese. One of its common charge states is +2, but there are other possible charge states for manganese, so I would have to use Roman numerals when I name it. Chromium forms quite a large variety of different charge states, but one of the most common ones we see is chromium 3. I still have to use Roman numerals because that's not the only charge state that's possible for it. So start to learn some of these other common charge states as you continue with the transition metals, but I'd recommend learning the ones that you see here first before you start to worry about the other transition metals. This will help you with quite a few different compounds you may have to name when we start naming ionic compounds, which consist of cations and anions. We're going to practice a few questions to see if you can read a periodic table with respect to things we might ask you. First of all, here's some of our example questions. The first one is, which element is a halogen in the third period? Okay, so would that be fluorine, chlorine, bromine, iodine, argon? Immediately I can exclude argon, right? Choice E. Argon would be in our last group here. It's a noble gas, so I know it's not argon. Okay, the next thing I need to do is recognize the third period. That's going to be the third row on the periodic table, starting here with sodium. Then I need to know that it's a halogen, so it should be here in in group 17 or 7A. So if I look at that, then I'm in the third period. It's a halogen, so it must be chlorine that I'm talking about. Okay. With these practice problems, what you might want to do is pause the recording, try to answer before I give you the answer to the problem. So here's our next question. Which element is a noble gas in the fourth period? So the fourth period is going to be our fourth row on the periodic table, correct? So that would start at potassium. Now we want it to be a noble gas, so I should recognize the noble gases are starting at helium. That's going to be my 8A or 18 for my column designation. Okay, so I'm going to look at the fourth period, over to the noble gases, and we'll see that would be krypton. Krypton. Now the next question I have for you is, which element is a fifth period alkali earth metal? Fifth period alkaline earth metal. So if we're looking at this one, we have to realize the alkali earth metals are going to be in the second column, the second group or family, starting at beryllium. If it's a fifth period, that would be my row on the periodic table. So the only element that would fit that description would be strontium here, strontium. So our next question would be, which fourth period transition metal produces only +2 charged stable cations? Okay, so this requires you to think about the cation charges for the monoatomic cations that we've been looking at. If we're looking at transition metals and we're looking at only one possible stable charge, there's only a few of them that you are expected to know that would form only one charge that was stable. So the fourth period starts at potassium. So we're starting at potassium. And so I go over to calcium. I'm not to the transition metals when I'm at calcium yet, right? That would be the alkaline earth metals. Then I go over to titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. I have to think about these transition metals. Were there any of them you should know has only one stable charge state? I told you to remember that stair step, right? Near aluminum, there's aluminum, zinc, silver. So zinc forms only one possible charge state. It was a +2. So I should remember that zinc's a +2, so that would be the fourth period transition metal that meets our description. So this may take a little practice. Maybe use some flashcards to learn your charge states and learn your portions of the periodic table. Quiz some other friends or family members, get in some study groups. That'll help you practice these types of questions. Now the next question I have for you is, what third period element is expected to form +3 charged cations? +3 charged cations. Now we're looking at period 3, and we're looking at cations, so that's probably going to be a metal, right? We expect metals to form stable cations. So we have sodium to begin with in period 3, but we know it's an alkaline metal. It would form a +1 charge, right, in that group 1. Then we have magnesium, right, and magnesium in group 2 will tend to form +2 charged cations. And then as we go over to aluminum, you notice that 3A becomes useful here at the top. That 3A rather than 13. The 3A reminds you that it forms a +3 charge, just as a mnemonic device here. So we should see period 3, aluminum would be the stable +3 charged cation that we're predicting here. Now, if we want to look at which third period element is expected to form +2 cations, we just answered that, right, just a minute ago. We know that if we're looking in the third period, we're starting at sodium, and sodium forms a +1 charge, so we go over to magnesium, and we know that the alkali earth metals would form +2 charges. So it's magnesium that forms a +2 charge. Now you probably could have predicted the next question. I'm asking you here, what third period element is expected to form +1 charged cations? Third period again, so we're dealing with alkaline metals. This is sodium. So we have sodium forms a +1 charged cation. Okay, so let's look at anions a little bit here. What fourth period element is expected to form a -1 charged monoatomic ion? I'm keeping things simple so that we're not looking at any polyatomic ions right now. So it's going to be a monoatomic ion, the ones I've asked you to learn first. So a negatively charged monoatomic ion in the fourth period. If I'm looking at that, I have to think about which type of elements tend to form anions or negatively charged species. Most likely culprit is going to be a nonmetal. Nonmetals tend to form negatively charged anions. So if I'm looking at a nonmetal that tends to form a negatively 1 charged stable monoatomic ion, well, what would fit the bill is a nonmetal that's 1 away from the noble gases. That would be in the halogens, correct? So that would be in my, that would be in column 7A or 17. So if I'm looking in the fourth period, and I'm looking in the halogens, that would be bromine forming bromide, a negatively charged, -1 charged monoatomic anion in that case. Now, if I want to look at the second period element that's expected to form a negatively 2 charged monoatomic ion, well, following the same reasoning, it's probably going to be a nonmetal if it's going to be stable. Okay, if it's negatively 2 charged monoatomic ion, it should be 2 away from the noble gases. So remember, my halogens were -1, so if it's 2 away, it's going to be something like oxygen, sulfur, or selenium. So I have to look at the second period, the second row. That starts at lithium. So oxygen is the one that's going to fit the bill here. It tends to form a negatively 2 charged monoatomic ion, and so that's the correct answer. Now, if I want to know what second period element is expected to form a negatively 4 charged monoatomic ion, it's probably a nonmetal if it's an anion, as we said before. If it's negatively 4 charged and it's a monoatomic ion, it should be 4 away from the noble gases. So if I count over 1 to the halogens, 2 to oxygen, 3 to nitrogen, and 4 to carbon, I expect carbon would have to gain 4 more electrons to get a -4 charge. We'd call that carbide, right? So period 2, -4 charge would be carbide for carbon. Now along those lines, if I ask you which second period element is expected to form a negatively 3 charged monoatomic ion, now we need to have an element that's 3 away from the nearest noble gases. I know it's in the second period, so that's eliminating some other possibilities. So if I look over at neon in the second period and I count 3 away from neon, so like fluorine, neon, fluorine, there's 1 away, oxygen's 2 away, nitrogen's 3 away. We expect nitrogen will form a negatively 3 charged anion that we would change the ending to an ide, right? So nitrogen goes to nitride. So there's my negatively 3 charged monoatomic ion atom I would expect. So nitrogen would tend to gain 3 electrons to form a negatively 3 charge. So here's another question. Which 5th period transition metal produces only +1 stable cations? Now I said it's a transition metal, so we know we're going to be here in this purple block, right? And so that transition metal that forms only +1 stable cations in the 5th period, that starts at rubidium, right? So I'm looking over. Now quite a few of these we didn't have rules for, so we're going to assume they're going to form multiple different charge states, so that's not what we want. So I want to keep going to the right until I find one which we had to memorize would only form +1 charged cations. If you recall, silver forms +1 charged cations, and that's the only stable cation we expect to form from silver. If you remember that stair step, silver is +1. Zinc, if we go up and to the right, is +2. Aluminum, as we go up to the right, is +3. So it's that +1, +2, +3 you should have memorized. Now, if I ask you which element is the 3rd inner transition metal in the 7th period. Now, realize I'm saying we're in the 7th period. We're looking at an inner transition metal. Okay, so the 7th period, we would go to the actinides. And if it's the 3rd inner transition metal in the actinides, the inner transition metals here, we'd be looking at uranium, right? Atomic number 92 here. This would be my 3rd inner transition metal in that 7th period that I should know. Okay, with this in mind, let's see if you remember what a semimetal is. Which is a 3rd period semimetal? Okay, so if I'm a semimetal, remember those are the metalloids. They're in green here. So my 3rd period, going over to be a semimetal, that'd be silicon. Now realize your periodic tables on the test won't be color-coded, so you need to kind of know these regions without seeing the colors. But here it's easy to remember that that would be silicon. Let's try this one. Which 5th period element produces stable diatomic molecules? So I want to know which one of these elements tends to form diatomic molecules. This is where I told you to remember the rule of 7, right? So we had nitrogen, oxygen, fluorine formed diatomic molecules, chlorine, bromine, iodine, and hydrogen formed diatomic molecules. So if we look at the 5th period and we go over it, that would fit the bill at iodine being our diatomic molecule that we would expect to form. Okay. The next question I have for you is I'm asking which of the following is a representative element? Remember, representative elements are also called main group elements. Those are the groups, the columns, the families that we had labeled with A's on the periodic table, right? So we exclude the transition metals, we exclude the lanthanides and the actinides, the inner transition metals, and we're looking at just the main groups. So since I'm excluding the transition metals, let's think about this. Well, if we look at tin, well, tin would be a main group element, wouldn't it? It's not a transition metal. However, if we look at iron, iron's a transition metal. If we look at gold, right? If we look at gold, it's a transition metal. If we look at uranium, that's an inner transition metal, right? If we look at silver, that's a transition metal. So the only one that fits the bill here is tin. Tin would be considered a main group element, right? It's under carbon and silicon and germanium. And we know it tends to form +2 and +4 charged cations, what we've looked at before. Okay, so this is the last example question that I have for you for this tutorial. It's very simple though to design more of these and test your friends in your groups, your study groups, come up with additional questions. Make sure you can label all these different regions of the periodic table and you can identify where certain elements might belong with respect to similar example problems. The test, you'll likely see some similar things to this. Sometimes I have a table designed to have you fill in with respect to which families and which periods and which portions of the periodic table you would predict an element to be at and give the element symbol or give the element name. So just keep practicing. Thank you for listening to this tutorial. Hope it helped you out. Let me know. Give me some feedback if you find them useful.